The potential energy of a dipole in an electric field. So we have seen about the electric dipole, what is the uh, electric field of a dipole, equatorial axis, on the axis of the dipole we have already seen. But we are about to see the potential energy of this dipole in an external electric field. So we are interested in potential energy. So if you see here, this is an electric dipole. We have A here, B here. So at A there is a minus Q charge, at B there is a plus Q charge, and the distance between this A and B, this AB, is 2A, right? Now this electric dipole is placed in uniform electric field. You can see that these lines are equidistant, so this shows that this is having a uniform electric field E, and the direction is X. The direction is X. That means the axis of the dipole makes some angle. Say let's make some theta. This theta angle, this one. This is dipole. This is electric field. This is the theta angle they are making. So its dipole moment will be simply Q into 2A. We know that the charge is Q, the distance is 2A. The dipole moment will be Q into 2A, and the direction will be in this direction, AB of the dipole. The electric potential energy of this dipole, what is this? This is will be the algebraic sum of the electric dipole energies of both of these charges, minus Q and plus Q. What we will see, will take arbitrarily the potential at the position minus Q as 0. So its potential energy, we are just taking it. You will just know that why we are taking it. We are taking the potential here at the position minus Q as 0. So the potential energy also becomes 0. Now we will try to find out the potential energy of this plus Q with respect to this minus Q, and this will become the potential energy of the whole dipole. The electric field is only in X direction. So what, as you see here, electric field is only in X direction. So what do we get here? Electric field E is given by minus del V by del X. And what is this del V? Del V is the difference in potential between this A and B because of these two charges. So del V will be VB minus VA by the delta X. Delta X is nothing but the distance like this here. And we are going to see AC. You will be amazed that we have to take this distance, but we are not taking this distance, but AC. AC is the distance because the electric field is in this direction and the dipole is in this direction. So we have to take the cos component of this, that is AB cos theta. This is AB is 2A, this is theta, so this will be 2A cos theta. This distance we have to take between Q minus Q and plus Q because we need to take this in the direction of E. So we will take AC as 2A cos theta, and we have arbitrarily assumed that this VA is 0. So this becomes only minus VB by 2A cos theta. So what will be VB? Just take this on this side. So VB becomes minus E into 2A cos theta. This is the potential VB. Now how to find the U, that is the potential energy? This can be found out by just multiplying this charge Q with VB. Potential energy is Q into the potential. Potential energy will become Q into VB. VB just found to be minus E 2A cos theta, put it here. And this Q, bring Q and 2A together, and this Q and 2A is nothing but the dipole moment. So we can write E. So what is this? E P cos theta. And what is this E P cos theta? This has to be E dot P, because E dot P, the dot product is E P cos theta. So this U becomes E dot P and minus sign. So the potential energy because of this entire dipole is nothing but minus E dot P. This is the value. So what we should note here, because cos is involved, so the axis of the dipole is normal to the electric field, that is theta equal to pi by 2, that is This is electric field and this is the dipole. Say minus q plus q. This is 90 degree. So when this is 90 degree, this E dot P will become EP cos theta. Theta is 90 degree. So cos 90 is 0. So this potential energy of a dipole becomes 0. And if it is parallel, say if this is the electric field line and this is the dipole, say this is minus q, this is plus q. The axis, because they are making 0 angle with each other, so it will be cos 0 here. It will be simply theta is 0, so simply it will be minus PE. The axis of the dipole is parallel to the field. AB is parallel to E here. If you see, AB, if it becomes parallel to this AC, then the dipole will become just simply minus PE. Now, if this has become minus PE, this is the minimum value of potential energy. So, dipole actually tries to arrange its axis parallel to the electric field. Everything wants to be equilibrium and gain or have minimum energy. So, it will try to align to the direction of the electric field. So, this dipole moment P becomes parallel to E. So, this in this state we say that the dipole is in stable equilibrium when the axis of the dipole and the electric field dipole or the electric field on this dipole, they are parallel. As I just said, any system will always try to remain in a state where the potential energy will be minimum. If you make theta equal to minus pi, that means if this is in this direction, means if you rotate this, plus q here, minus q here, then it will be in unstable equilibrium. So we have to see about the charge also, because we have to understand that the electric field is in which direction.